So in the previous lesson, I talked about how to determine the rate law for reaction if the first step is the rate determining step, is the slow step. And so I want to review this concept really quickly and why we use the slow step in writing our rate law. So I'm going to use an analogy. Here you've got cars and you've got toll plazas. Now, if you think about it, if toll plaza A is the rate determining step, what that means is that because the teller is so slow, it dictates the amount of traffic. Now, in contrast, if toll plaza B is the rate determining step, then what that means is that toll plaza A, cars can just speed through toll plaza A, so it doesn't dictate how many cars can get through to point 3. Instead, it's toll plaza B. And so this analogy is important because just like toll plazas, whichever reaction, whichever elementary step in your reaction mechanism is the slow one, that's going to determine the rate at which your reaction proceeds. And therefore, that elementary step is the step that should be used in determining the rate law. So in the previous lesson, it was really easy because your rate determining step was the first one, and so you simply wrote out the rate law based on the stoichiometry, and there was your answer. Now the issue arises when your initial step is fast and not slow, and this is why. Let's look at an example. So in this example, as you can notice, your slow step is going to be step 2. And so what ultimately happens is there's a backup, because imagine that these are 3 different toll plazas. Because toll plaza 2 is so much slower, you're going to end up with a backup at toll plaza 1. And this is actually going to be helpful for us in determining your rate law. And so what we're going to assume is that at step 1, even though it's fast, because there's a backup, because step 2 is so slow, step 1 is going to exist in equilibrium. Remember, at equilibrium, the rate of your forward reaction equals the rate of your reverse reaction. And so we're going to use this. Now, here's where the issue lies. Based on what you learned in the previous lesson, what you should be able to do is simply take step 2, that elementary step, and use its molecularity in order to determine its rate law, meaning rate equals K times the concentration of X times the concentration of B. Well, what you should notice is that X is actually an intermediate, and you cannot use an intermediate in your final rate law. And so what we're going to need to do is use the fact that step 1 is in equilibrium to our advantage. So let's look at these steps. The first thing you got to do is look at the step before the slow step, and you're going to write the rate law for both the forward and the reverse reactions, and you're going to set them equal to each other. And that's because they're in equilibrium. So for step 1, it would be the rate for the forward reaction would be K, your rate constant, times the concentration of A squared. And I'm going to set that equal to the rate of the reverse reaction, which would be K2, for example, times the concentration of X, because in the reverse, X would be your reactant. Now, I can isolate my intermediate, and the way I can do that is simply dividing both sides by K2. So what you would have would be K1 divided by K2 times the concentration of A squared. Well, here's a cool thing. Since I don't actually know my rate constant yet, I can simply say K1 divided by K2 is just K. And so what I get is that X equals K times A squared, the concentration of A squared. Now I can take that value and plug it in for X. And so as I had said before, the rate for this second step, for the slow step, would be rate equals my K times my concentration of X times my concentration of B. And so what I can do is I can simply take my concentration of X that I got in step 2 and plug that in for the X in the rate law. And so what I end up getting is that my rate equals K, because K times K is just K, times the concentration of A squared times the concentration of B. And that, as you notice at the very top, is the rate law that was given to you. So you were able to use stoichiometry and these elementary steps in order to determine your rate law.
All right, so let's look at one more example of determining the rate law when your first step is not your slow step, when your second or your third step is your slow step. So here I give you a 3-step mechanism. Notice that step 2 is going to be your slow step, all right? So first of all, it asked me to write my overall reaction. So I'm going to sum up the reactants and the products. So on the reactant side, I have Cl2, and it reacts with chloride, but you have two chlorides, two Cls, because you've got a Cl from step 2 and a Cl from step 3. And you've got CHCl3 and CCl3. All right, so those are your reactants. For your products, you've got 2Cl plus HCl plus CCl3 plus CCl4. All right, so now let's simplify this. So I'm going to get rid of anything that exists on both the reactant and product side. So I'm going to get rid of my Cls, and I'm also going to get rid of my CCl3s. And so my overall reaction is then going to be Cl2 plus CHCl3 produces HCl and CCl4, all right? Well, what are my intermediates? Well, remember, if you cancel something out in a reaction, it could either be an intermediate or a catalyst. Remember, an intermediate is going to be created during the course of the reaction and used up. Meanwhile, a catalyst exists at the beginning of the reaction and at the end of the reaction unchanged. So CCl could be an intermediate or a catalyst, and same with CCl3 since I canceled them out. So let's look at Cl first. Notice Cl is produced in step 1 and then used up in step 2 and step 3. Therefore, I know it's going to be an intermediate. My other intermediate, notice CCl3 is produced in step 2 and it's used up in step 3. Okay, so those are my two intermediates. If a question asks you to explain how you know it's an intermediate, all you need to say is it's produced during the course of the reaction and it is used up. All right. What is the rate determining step? Well, I know my second step is my rate determining step because it's my slow step. Okay. So then to write my rate law, I'm going to start off by simply writing the rate law based on the stoichiometry from step 2. So it would be that the rate equals K times my concentration of Cl times my concentration of CHCl3. However, since Cl is an intermediate, it cannot stay in that rate law. So here's what I'm going to have to do. And notice I ask you to explain, and you might be asked to explain. So just showing your work won't suffice. So first, I use the stoichiometry of the second step, as I just explained, since it's the rate determining step. To replace Cl, since it's an intermediate, and step 1 is an equilibrium, remember the step before the slow step is going to be an equilibrium, the rate of the forward and the reverse reactions are equal. Therefore, okay, so I've explained, write your rate law based on the stoichiometry for your slow step, but then since Cl is an intermediate, you need to replace it. To replace it, set the rate of your forward and reverse reactions for the step before equal to each other, and then I show it. So I show that the rates of the forward equals the rate of the reverse. Notice the forward reaction for step 1 would just be K times the concentration of Cl2, which equals the reverse with K times the concentration of Cl squared. Then I need to isolate Cl. So concentration of Cl all by itself would be K times the concentration of Cl2, but I've got to square root it since my Cl, the concentration of Cl was squared. So I'm going to raise that to the 1/2. Now that I've isolated my Cl, then I can simply plug it back in for rate equals K times my concentration of Cl2 raised to the 1/2 times my concentration of CHCl3, and I've got my answer there.